Good morning all. Module for Geotechnical Engineering 1. These are the contents: the compressibility and consolidation, in which we will discuss the coefficient of compressibility and volume compressibility, compression and recompression index, NCC and OCC, estimation of pre-consolidation pressure, magnitude of settlement of NCCs, and a few numerical problems. Besides that, we'll have a brief discussion on the Tesage's theory of one-dimensional consolidation. These terms, time factor, average degree of consolidation, coefficient of consolidation, etc. will be dealt with. We'll have a few practical applications, and lab consolidation tests will be briefly discussed, and with square root of time and log time fitting methods, and a few numerical problems will be included. Later on, we'll have a discussion on the compaction of soils, in which standard Proctor, modified Proctor's light and heavy compaction tests will be discussed, OMC and zero over Ward's line, and a few numerical problems as well, besides control of compaction in the field. Now, the ones that are marked and highlighted yellow are the additions compared to the previous semester syllabus. So the compaction of soil is one addition that you have in this module compared to your senior batches. Now we'll start with the first term, consolidation of soil. Whenever you get a mark list in your 8th semester, you will get an individual mark list of the 8th semester plus what we call as a consolidated mark list, in which all the grades that you have earned over 8 semesters will be consolidated to one single mark list. Likewise, consolidation is one such property of soil, clay soil to be specific. Before that, we'll try to understand compressibility. The term compressibility. Compressibility is a property by which there's a decrease in volume under a compressive load. When you apply a compressive load, the material onto which this load is applied gets compressed. So this decrease in volume may be due to, number one, the compression of solid and water, or it can be due to the compression and expulsion of air, or it can be due to the expulsion of water. Now, you see a picture to the right side in which you squeeze a sponge which is filled with water, soaked with water. So consolidation, the one that we are interested in this module, is a reduction in volume of the soil due to the expulsion of water under a static pressure. And these two terms are quite important. Expulsion of water. The volume reduction is not due to the compression and expulsion of air. It is not due to the compression of solid and water. Instead, it is due to the expulsion of water, and it is under a static pressure, not a dynamic pressure. So the settlement and the gradual sinking of structures resting on soil, clay soil to be specific, could be due to consolidation most of the times. You see a picture in which you see a crack being propagated through the wall, and it probably may be due to the differential settlement. One side of the building gets settled more than the other side. So these settlements and the gradual sinking of structures is part of an effect of consolidation usually. Now to discuss the few terms that's included in your syllabus, we'll start with the laboratory consolidation test. Now, consolidation procedure is quite simple. You take the soil sample and keep it within a set of porous stones inside what we call as a consolidation cell. So this is a consolidation cell. The cross section in schematic is shown here, and the actual photograph is shown here. So basically your intention is to squeeze the soil and to see the rate at which there's a reduction in volume. So consolidation basically is a reduction in volume. It is due to expulsion of air, it's due to expulsion of water, and it's due to a static load. So we have a mechanism by which you apply a static load here, and the load frames comes over what we call as a consolidation cell, and the load frame is attached to a lever arm in which you can have option to have dead weights. So the dead weights that you place on the lever arm gets transferred through the load frame and acts on the consolidation cell's top cap. So the top cap is resting on the porous stone, and the porous stone is over the clay layer. So the soil sample is kept between a set of porous stones, sandwiched between the porous stones inside the consolidation cell. Now you have the loading pad or the top cap, and it's kept above the assembly and placed in a loading mechanism, and an initial stress of seating load is applied. Now once that seating load is applied and the next load increment is given, and the dial gauge recordings are noted down at proper intervals. So you have a dial gauge here. A dial gauge fundamentally measures the deformation over the soil. Now the dial gauge is resting on the top cap or the loading pad, and when it settles, the dial gauge shows a reading. So once we apply the seating load, the next step is to apply the first load increment, and when you apply the first load increment, you can see there's a change in the dial gauge reading. Now this is noted down against a time frame. Usually you take dial gauge readings up to 24 hours, and in the initial set of readings the settlement will be faster, so it'll take at proper intervals. For example, once you keep the load, you'll take dial gauge readings of 15 seconds, 30 seconds, 1 minute, 2 minutes, 4 minutes, 8 minutes, 15 minutes, 30 minutes, likewise. So you'll continue up to usually 24 hours, or when the settlement rate is quite negligible. And then you apply the second load increment, and you note down the dial gauge readings quite similar to the way that you had did earlier. And the water is allowed to pass through the sample till the test is finished. A sample is then taken out and kept in the oven for water content determination. So essentially what you do is you squeeze the soil sample using a static load, and you allow water to escape out. So as water escapes out, the soil particles gets compressed together, which means the void spaces gets reduced, and there will be a reduction in the total volume of this layer. So this reduction in volume is represented in the reduction in the height from the settlement gauge or the dial gauge. So as the volume reduces, it means that the height of the sample reduces, because it's one-dimensional consolidation. The circumference is restrained. So the only option for this soil sample to reduce in volume is to get reduced in height. So the reduction in height due to the static load is measured from the dial gauge over time. Now the types of consolidation. Number one is the initial consolidation, which happens just after the application of the load, and it's mainly due to the compression of solids in saturated soil. Now in partially saturated soil, it could be due to the expulsion of air as well. The second is the primary consolidation, which is predominantly due to the expulsion of water. Now the primary consolidation is the one that we are actually interested in. Now, initially the load is taken by water, and as time progresses, water escapes out and the load is transferred to the soil. Hence, the permeability of the soil is a major factor which influences the time taken for consolidation. When you have high permeable soil, the time taken for consolidation will be quite low. So primary consolidation is quite quick in coarse soil, coarse grained sand. Next one is the secondary consolidation, which is of a slow rate process compared to the earlier ones, and it's mostly due to the plastic readjustment of solids. Now moving to the consolidation test results. The data from the lab that you get, a sample is shown here. Initially you'll have a stress applied on the loading pad, the first one being the seating load, let's say 0.5 kilopascal, just an example by the way. And you'll be given with a stopwatch, and time t equal to 0 means the time at which you have placed the stress on the loading pad. So corresponding to time t equal to 0, there will be a dial gauge reading, and of course the settlement delta H will be 0. As time progresses, let's say 15 seconds or 0.25 minutes, you will have one dial gauge reading there, which will be different from the initial one. So obviously it means that there's a settlement in millimeters. Likewise, you'll take the dial gauge readings corresponding to times 0.5 minute or 30 seconds, 1 minute, 2 minute, 4, 8, 16, 30, 60 minutes, which is 1 hour, then 2 hours, all the way up to 24 hours, or when the settlement is very negligible. Now this entire reading corresponds to just one load or 0.5 kilopascal stress. So for 0.5 kilopascal stress, you will have a number of dial gauge readings. Correspondingly, you will have settlements shown here. So settlement is nothing but the change in dial gauge reading. And once the effect of the single load increment is finished, which you can, by the way, infer from the dial gauge reading. If there's no significant change in the dial gauge reading, let's say after 4 hours, it means that the effect of this particular load has almost reached 0. At that point, you can place the second load, let's say 1 kilopascal or 1.5 kilopascal, for example. And for 1 kilopascal, you'll have again a table like this in which you'll mark the dial gauge readings and the time elapsed in minutes. Of course, there will be settlement, which you calculate from the differences in the dial gauge reading. Now, this is a typical data that you take from the lab. So basically, once you complete a test, the reading that you take will be the time and the dial gauge reading. From the dial gauge reading, you can find out the settlement or delta H. This is an initial sample of clay, cross-sectional area A, and let's say the initial height being H0. So when you mark delta H, it means there's a settlement. So the clay sample after load increment will probably look like this, with a reduced height of H0 minus delta H, where delta H is a cumulative change in the dial gauge reading or the total settlement corresponding to one single load. So you have an initial clay sample whose height is H0. It got squeezed or consolidated where the water got expelled out and the solid particles came together in a more packed fashion, and now the height is H0 minus delta H, where delta H has a settlement. There will not be an increase in area because it's one-dimensional consolidation. The clay sample is restrained to expand sideways. Now, to determine the void ratio during the test, you have a few methods. As time progresses, the water from the voids gets expelled under the static load, which of course is what we call as consolidation. And this in turn means that the void decreases and hence the void ratio. Let's assume that there's an initial void ratio of E0, and when the sample got consolidated from a height of H0 to H0 minus delta H, there'll of course be a change in void ratio as well, because the solids got packed, and the change in void ratio is a decrease in void ratio, and this decrease in void ratio is nothing but the one that you get a reflection as the change in height. There are two methods to find the void ratio during the test. Number one is a height of solids method. Void ratio basically, by definition from three-phase system diagram, is VV by VS, volume of voids by volume of solids. So that's V minus VS by VS. V minus VS is nothing but the volume of voids. So numerator is V minus VS by VS. So when you take this particular sample, the volume is A multiplied by H. So I can replace volume as H and volume of solids as HS. So V equal to H minus HS by HS, because area remains the same. H being the total height or thickness of the soil, and HS being the height of just the solids. This is a mathematical concept that we'll discuss. Initial height H0 of the soil specimen is usually 25 millimeters or 2.5 centimeters is the usual range of the height of the sample of clay that you keep in the odometer. And from the top area of the soil specimen, you can calculate the height of solids as HS equal to VS by A equal to MS by rho S into 1 by A. So like I said, it's a mathematical term as explained here. Height of solids, volume of solids by area. I can replace volume of solids by mass by density of solids, and the density of solids is rather represented by specific gravity multiplied by the density of water. So in short, HS will have a representation as MS by G rho WA. HS equal to VS by A equal to MS by 0 WA, and E is H minus HS by HS. These are the two relations that we have now. Now, based on which you can calculate the void ratio as H minus HS by HS, where H is already known. HS corresponds to this equation. So when you have an applied stress, you'll get the dial gauge reading, from which you'll get the change in height, and the change in height will give you the height H at each stage of the applied stress. So HS is already known, H is known, from which you will get the void ratio corresponding to one stress applied. Now the second method is the change in void ratio method, where we go back to the three-phase system diagram. You have three phases, soil, water and air, and volume of solids is replaced by unity, which will give you the volume of voids as void ratio itself, and the total volume as 1 plus E. So this is a basic concept that we introduced in the first module for us to derive a few basic relations. So we'll make use of this figure, the three-phase system diagram, where the volume of solids is unity, from which we already know basic relation SE equal to WG. But in this particular case of consolidation, we mentioned that the soil will always be saturated because you allow water to pass through it throughout the test. So S, or degree of saturation, is unity, which means SE equal to WG, where you can represent E equal to WG as well. Now from the three-phase system diagram, volume is 1 plus E, and since area remains constant of the soil sample, H equal to 1 plus E is also a logical representation. Volume can be replaced by height because area remains constant, and the change in void ratio is thus equivalent to the change in height, or delta H will be equal to delta E. From this, you can take the ratio of delta H by H as delta E by 1 plus E. Delta H by H equal to delta E by 1 plus E, or delta E equal to delta H by H multiplied by 1 plus E, where delta is a change in void ratio. So knowing the initial height of the sample H and the change in height from the dial gauge, the change in void ratio delta E can be calculated. This, when subtracted from the initial void ratio, gives the void ratio corresponding to a particular load increment. So the second method that we discuss here is based on the change in void ratio, where you find the change in void ratio from the change in height, and the change in void ratio will give you the void ratio corresponding to a particular load increment.